Good morning to our colleagues who are joining us today from California. Good afternoon to IEEE members who are joining us from Europe, and good night to attendees from India and China. So welcome to the UMaine Artificial Intelligence webinar series. My name is Ali Abedi. I'm Associate Vice President at the University of Maine and also serving as Region 1 Northeastern Area Chair. The topic of our discussion today is on education and workforce development. So it's my great pleasure to introduce our first speaker today. Dr. Yifeng Zhu is the Libby Professor in the Department of Electrical and Computer Engineering at the University of Maine. He received his PhD and master's degree from Department of Computer Science and Engineering at the University of Nebraska-Lincoln, and BS from the Department of Electrical Engineering from Huazhang University of Science and Technology, China. He has worked on big data storage systems, emerging memory technologies, and high-performance computing. Recently, he worked on the application of AI in medical imaging analysis and scientific applications. He received the Best Paper Award in Cluster 2007 and Best Paper Award nomination in HPCA 2012. He wrote a textbook on embedded system, which has been adopted by over 90 universities worldwide. So without further ado, let's welcome Yifeng to the podium, and please keep your questions posted in the Q&A session. After all three talks are over, we will answer your questions. So Yifeng, the floor is yours.
Thanks, Ali, for the introduction. And thanks everyone for attending this seminar talk. The title of my presentation is AI and its future work in medical imaging. I'm sorry that I have to teach my class in half an hour, and that I won't be able to stay here during the Q&A session at the end of this seminar. But if you have any questions, and here is my email address, and please feel free to contact me directly. Here is the timeline of AI. Since the 1950s, a small subset of AI, also called machine learning, has revolutionized several fields over a few decades. After that, machine learning has passed through two winter periods. Currently, machine learning is facing its third boom time. The third boom is mostly powered by deep learning, or called deep neural network, which is a subset of machine learning. And deep learning has been creating ever larger disruptions and generating tremendous success in a variety of application domains. And many people think deep learning begins with AlexNet, which is proposed by a research group at the University of Toronto in 2012, the AlexNet. The AlexNet contains only 8 layers with 61 million parameters and over 600 connections. Nowadays, many deep neural networks are much larger and deeper and contain hundreds of layers and much more parameters. The effect of AI is already here. And in 2016, an AlphaGo built the world champion, and since 2017, not champion, the 9-dan professional player. And since 2017, DeepMind introduced a total new version, which is called AlphaGo Zero. So it's becomes even more powerful. And many big tech companies such as Tesla, Waymo, Apple, and Uber, they all are actively developing self-driving cars. And Boston Dynamics designed mobile robots for moving boxes in the warehouse. They use deep learning algorithms to identify and locate boxes. In healthcare, AI will have great impacts on the performance and efficiency and the quality of patient care. As of today, FDA has already approved over 60 AI or ML AI-based medical devices and algorithms. The global market size for the AI in healthcare is projected to exceed 31 billion by 2025. The question is why machine learning, especially deep neural network, becomes so powerful now. In the 1980s and 90s, with limited amount of data available and limited computation capability, conventional method achieved much better results than neural networks. Now we have more data and much more computation power. According to a recent report published by IDC, International Data Corporation, the amount of data worldwide is doubled every 3 years. This is not surprising as we have entered a digital world. At the same time, we have more computation power and more memory bandwidth due to the benefits of the Moore's law. As a result, now it becomes realistic to train a very large, a very big neural network on a huge data set. Accordingly, deep neural networks outperforms conventional approaches in many fields, such as computer vision, text and speech, and autonomous driving. For example, in the ImageNet competition, a deep neural network can achieve much lower classification error than humans. And ImageNet has have over 14 million images, and they are classified into one of 1,000 object categories. For example, this image is classified as still drawn. And human classification error is approximately 5%. And in 2015, and ResNet 152 achieved a classification error of 3.6%, which is better than the human. It's really cool that deep neural network can learn very complex functions, which cannot be learned before. We can simply consider the function as a complex mapping from given inputs to their desired outputs. Around 10 years ago, people started to use deep learning to attack computer vision problems such as image classification, object localization, semantic segmentation, and image synthesis. We can feed raw image values to a deep neural network, and the network can automatically learn underlying features in this image and recognize the objects in the picture, such as panda. We can also feed raw audio waveforms and let network learn what's being said in the waveform and may even translate it to a different language. We can also train the network to learn how to describe an image in natural languages. For example, in this picture, if this picture is given to the network can output the sentence, an elephant is eating a pumpkin. Advances in deep learning have great potential in transforming the medical field. Especially, it will greatly impact the future of medical image processing and analysis. Healthcare providers are generating and capturing enormous amount of data containing extremely valuable signals and information. And deep learning, therefore, quickly enters the picture. And it's one of the best approaches to automatically analyze and make predictions on large data set. This figure is obtained from a paper called The State of AI-Based FDA Approval, Medical Device and Algorithms, which is published in the Journal of Nature Digital Medicine this year. In 2016, FDA approved the first AI-powered software, and there are at least 64 AI or machine learning-based medical devices and algorithms that has been approved by FDA, and 22 of them are approved in 2019 alone. Majority of them are in the field of radiology, cardiology, and oncology. there are great opportunities for AI or machine learning. And certainly, there are also great challenges as well, such as regulatory framework and trust issues with new technology. My research group has investigated deep learning technologies to detect breast cancer and lung cancers. In clinical practice, a tissue biopsy is cut into very thin slices. And then they use chemical to color the slices. And then pathologists use a microscope to examine and analyze the prepared biopsy slices. However, reviewing biopsies for the evidence of a tumor and determine pathological stages is a complex, time-consuming, and also potentially error-prone process. If we digitize the biopsy sample, we can get a very large digital image. In fact, with the recent regulatory approval and gradual improvement of digital scanning systems, conventional glasses slices can be quickly digitalized into high-resolution images, which is we call whole slide images, or WSI. For example, under 40x power magnification, this digital image has over 20 gigapixels, which is equivalent to 1,800 photos taken by iPhone X. You can imagine that, find a small tumor area in such a large image under the microscope is not an easy job. It's really time-consuming and labor-intensive. And my research group has worked on exploring deep learning technology to assist the pathologists, reduce their diagnosis workload, and improve the diagnostic accuracy. So whole slide image is too large for deep learning network typically. So usually what happens is we have to extract small samples from the original image. We call these small samples as patches. So for example, for small tumor area, usually we extract patches in a sliding window fashion. And for large tumor areas, we randomly select patches. And here shows you some small patches extracted from the big image obtained at 40x magnification. Each patch has 500 by 512, 512 by 512 pixels. Patches from tumor area are shown on the left, and patches from normal tissues are shown on the right. There are two great challenges. First of all, even with extensive training, there's big substantial diagnostic disagreement among breast pathologists, leading to either over-treatment or under-treatment. For breast cancer, the average diagnostic agreement given by different pathologists for the same patient is approximately around 75%, as shown in these pictures. Sometimes it's difficult to identify the tumor. The second challenge is that pathologists often need to measure the size of tumors in order to classify cancers into the right stage. Measure tumor size manually is really time-consuming. AI-assisted technology can help solve these two challenges. It can improve the diagnostic efficiency and increase the level of inter-observer agreement. And here's an example of whole slide image scanned of stained sentinel lymph nodes. It has 10 gigapixels. The presentation screen can only show you a zoom out view, cannot show you the details. And this is the classification results. And you can see the tumor area has been we call this one as a heat map. And you can see the red area is correctly identified the tumor. And certainly the algorithm also makes some small false positive predictions, which are scattered around the image, which is some of the future work we're going to work on. And we also participated in the international competition PACIP in 2019. The goal is to segment whole tumor areas marked by yellow lines in the picture, and also the viable tumor area, which marked by green lines in this picture. We are also required to report the viral tumor burden for each host line image, which is defined as a ratio between the variable tumor area and the whole tumor area. There are around 800 participants and 64 submissions in this competition, and we ranked among the top 10. I was invited to give a presentation as a competition workshop. So we have designed a deep neural network to generate a probability heat map for each patch, and then this patch assembles the output. We use UNet++ with various backbones. The heat map of all patches are tied together to generate the final heat map for the slides. We have two main nodes in the network model and train process to optimize the segmentation accuracy. For example, extensive data augmentation has been performed to increase the diversity of the training data set, making the trained model is more robust to overfitting. And this is augmentation applied at runtime. Okay, and we also applied color jittering to overcome color variations. And you can see the left is the original one, the right is our augmented. And this picture shows the ground truth, compares the ground truth with different models outputs. And the red ridge indicates high probability of whole tumor. And we choose to use voting algorithms. And there are two types of vote, and soft vote and hard vote. And hard vote is more like the majority vote, and soft vote is more like a weighted sum. And for each pixels, we use the soft vote, which generates average probability. And so you can see here the voting in terms of three outputs, and it shifts much better results than each individual model. And we have published our, I forgot to mention that we have published our results have been accepted by journals of digital medicine. So we're going to, it will appear next year. And so since the topic is about education, I will spend quickly talk about I'm teaching deep learning, and this show you some interesting project we're going to perform by students. This is one example, student project, finding the weddles and using the deep learning network to detect the potato disease. So we have early bright and late bright and healthy. And we also use existing tools to look at, to check whether our network has looked at the right area or not, which is try to explain how AI work. And also try to use satellite image to predict the urban area. The expansion of urban area is a good measure of the impact on the ecosystems. So how to use machine learning to automatically detect the urban area. And also, for example, how to give a black and white image, how to generate a color image. And this is my conclusion. So I see deep learning has a very show great promise in medical images. And our research results shows it's very effective in spotting and diagnosing cancers. But however, it requires our interdisciplinary collaborations. So we need to train more students to work on this growing area. Okay, thank you so much.
Thank you for the great presentation. And if you have a couple minutes, I know you have to go teach your class. We have two questions. Do you want to answer them now or leave them for offline? Okay, so the first question from Brian Walker: how is your work similar or different than Google/DeepMind efforts?
Yes, Google has DeepMind has developed breast cancer, and we're different in that. However, their data is private. They don't release their data, so we cannot have direct comparison with their work. I think to answer your question simply, our difference is our model is different. So, but we cannot directly compare with them.
Thank you. And the second question is that, do you have any IP connected to your work?
We are working on, so we're developing our own IP currently. Yeah.
Okay, very good. Thank you again for the presentation. So let's move on to the next speaker. Our next speaker is Dr. Thorsten Hamann, who is an associate professor in the School of Computing and Information Science at the University of Maine. Prior to coming to UMaine in 2013, he received his PhD in computer science from University of Toronto, specializing in knowledge representation as one key sub-area of AI. His current research is at the intersection of AI and spatial information, with a particular focus on developing, studying, and using ontologies and knowledge graph as means to transform data into knowledge and for computers to reason and communicate more intelligently. He applies ontologies to improve management and sustainable use of natural resources, such as water, forest, and agricultural resources and products, and to help with disaster mitigation and management. His research is currently funded by USDA and NSF. He's a co-PI on a $5 million NSF Convergence Accelerator project on developing an urban flooding open knowledge network. So, Torsten, the floor is yours.
Yes, hello everyone. Thanks for joining us here. So I'm interested kind of in AI on a much broader scale. And so I'd like to talk a little bit about how AI research right now will inform AI education. And as we all know, AI skills are really some of the most sought after skills in the job market, and we would like to kind of improve the talent pool. But that's very hard, and it's a very kind of long-term task for us to do. So traditionally in computer science, we have been seeing like the trend that a lot of jobs have been filled by people that have kind of a self-taught programming skills. But this doesn't work very well for the AI area because it's a very deep and very broad area. And so to understand this a little better, I would like to talk about what AI all encompasses and where AI may be in like 10 to 20 years, because that is really like the horizon that we're looking at for education purposes. We want to train the AI scientists that can work on what is new and kind of the frontier of AI in that larger time frame. So one of the difficulties in defining AI is really what has been called the AI effect, that AI is really the things that are novel and things that we can now do, like beat a human at Jeopardy or chess, are no longer really considered AI, even though they're like great advances. So we're trying to push the boundary of what machines can do, and this kind of pushes our definition of AI as well. So as Yiping mentioned, like AI has really been around for over 50 years, and you might not notice or might not realize that we are using a lot of AI in our daily lives already. Like any search engine, navigation systems, like just getting from A to B, personal assistants on your phone, recommendation system for movies, for music, the personalized ads that sometimes are so eerily targeted to you, or just like communicating with an automated agent, like when you call a call center to kind of get help. And as Yiping also mentioned, like in our attempt to move towards autonomous driving, a lot of AI systems have actually found their way into our cars already, like automated braking systems, lane assistance, drowsiness detection, self-parking systems, etc. So there is a lot of AI already around. And AI is much more than just machine learning. So I'm personally kind of coming from a background in knowledge representation and reasoning. that has a long tradition in kind of expert systems, ontologies, knowledge graphs. But there are other large areas of AI that are still kind of making great progress and are needed to kind of advance the overall AI. So search, autonomous agents, natural language processing, computer vision. It's all kind of puzzle pieces of achieving like true intelligence. So where may AI be in like 10 to 20 years? So that will really inform what we have to do education-wise. So I've used this figure from DARPA that kind of talks about that shows the frontiers of AI. So right now we are kind of on the left side here, like what something that like narrow AI. It's really, really good at accomplishing a very specific but narrow task, just like image classification, like identifying objects on an image, or as Yiping talked about, like finding a cancer on a medical image, or playing a game like Go or chess. But the frontier will be moving towards what's kind of called machine common sense to kind of make this more robust and not just solve this one task, but actually see it in context. Like, does it make sense given like what I know, what I see around me, like given the situation? And really, the very long-term goal is what's that like general AI, where that's kind of resembled human level intelligence that can like put things together, put different algorithms, different approaches, knowledge together, and make like sensible and reasonable decisions. So even so, there's a like a big hype right now about machine learning alone. AI really needs to shift beyond that again to make the next advances. So to kind of inject common sense into our AI system to make them more acceptable, to make them more user friendly, like to decide, oh, this doesn't make sense what I've been asked, or the conclusion that I've come to is not doesn't fit into the context, and to kind of understand new situation and the context of things. And this is all tied to issues like most social issues, like robustness, fairness of AI system has been a huge issue, like to avoid kind of enhancing existing biases. And also the trustworthiness, like eventually AI systems will only be adapted if we trust them. Like a doctor will only use a system if he understands what's going on and if he thinks like he can trust the results. Another trend is kind of understanding explanations. So to explain how a decision is made, why, not just what, like this is an image of a dog versus a cat, but this is an image of a dog because I see this and this. And then transfer learning that kind of applies what has been learned from one situation to a very different situation. So based on kind of the history and where we think we're going, I've kind of assembled like four areas or challenges for AI education. So AI is broad, very broad. It's also interdisciplinary. It's not just computer science. It is very deep at the same time, and it is sensitive. Let me talk about these things briefly. So broad means that to do research, but also to apply AI systems and make them work for a particular content, not only requires kind of an undergraduate computer science degree, but much more than that. Like it requires knowledge of the different AI sub area. It requires both a solid mathematical foundation, like statistics, algebra, but also logic, algorithms, etc., and kind of more hardware focused things like how to make it fast and scalable. But then it also requires domain knowledge. So that's what I meant with AI is interdisciplinary. Like we cannot uh, develop AI in a vacuum. It actually kind of ties together what we know about language, for example, neuroscience, mathematics. So there are like a lot of things that are connected here, and we cannot just develop AI in isolation as like software systems because they won't be um, adopted and they won't be suitable for humans. So the third point that I wanted to make is AI is deep. So learning AI is like learning quantum physics. It's very challenging subject area and it's advancing rapidly. So it's very hard to actually stay on top of what the state of the art is. It needs advanced computer science and advanced mathematics. So it really requires like a deep foundation of understanding what the basics are. And even if we are just applying AI tools, we need to understand which tools are suitable for a particular problem and which are not. So we need to be able to adapt it to the problem at hand. So it's not yet just a black box. We actually need to understand it to change it. So that's why I said initially it's not very suitable to be self-taught, but it requires this long lead time, which makes it more difficult and more challenging to kind of grow the talent pool in AI. So the fourth point I brought up was AI is sensitive. So this figure here that I showed part of earlier from the Dutch AI manifesto also includes like these socially aware ethical aspects. As we've seen, like AI is deployed in very sensitive areas for healthcare, for law enforcement, military uses, where it's like life and death uh, decisions, and but also like industry operations, transportation, etc. So we really need to make sure that what we develop is trustworthy and is we can understand what is going on and we are okay with the decisions, how they come about. And of course, AI can also be used for malicious purposes like deepfake, cyber attack, etc. So we have to kind of deal with the downsides of that as well and be prepared to kind of counter that. But what's much more dangerous often are the unintended side effects, like the things that such as bias, social or racial bias, spread of misinformation that AI algorithms can foster without anyone actually wanting that. So we have to kind of think broadly and take kind of a lens from a distance to figure out, is this really what we want to do, or do we need to design our systems or algorithms differently? So from an education perspective, we really need to teach these ethical social aspects as part of a well-rounded AI education. So to kind of take these 4 points and sum them up into what can we do to broaden AI education? Well, there are two things that come to my mind. One is kind of on the short term, we can kind of base AI training education on the skills that people already have. So kind of, for example, somebody with a mathematics degree already has the deep mathematical foundation. We can add the kind of specialist AI computer science training, or somebody from a natural science background has the relevant domain knowledge to kind of help explain and understand AI deployed in that area. So we can kind of build on that. So we need to kind of develop specialized degrees that kind of complement the existing expertise and help us develop well-rounded AI scientists. So here at UMaine, there are some initiatives we are already undertaking. We're developing an AI track within the computer science undergraduate program, but we also expand our offering of AI-focused graduate courses to people that come in from different backgrounds and want to pursue like a master's, PhD degrees. And of course, we're also starting like a new data science degree that has significant AI components embedded, and that actually is tailored to people from various backgrounds. So we need to kind of be flexible here. In the longer term, to expand the pipeline for AI experts, we need to teach foundational computer science skills much earlier. And I think there's a nationwide push for that already, to kind of embed computer science in middle and high school curriculum, so that we can teach more advanced computer science in an undergraduate program, for example. But another aspect of this is also to rethink what kind of math we're teaching, like in K to 12. Is it still what we need? Like AI needs very different kind of math than what is traditionally taught, like with a heavy emphasis on calculus traditionally. So there's some initiatives as well that we are pursuing right now. We're working with middle school teachers to integrate computer science into the middle school science curriculum, to kind of have this early exposure, and developing some graduate certificates in computer science education, so that teachers are actually able to bring this to their school. So these are just first steps, but I'm optimistic that we can make progress towards broadening AI education, but it will take a lot of effort. So thank you very much, and I'm happy to take questions later on.
Thank you very much, Torsten, for the great presentation. So in the interest of time, let's move on to the next presenter, and then we'll answer the questions which are being posted on Q&A at the end of the talks. So our next speaker is Dr. Walter Rall, who serves as the chair for IEEE main section and on the 3 IEEE USA Congressional Policy Committees, Artificial Intelligence and Autonomous Systems, Research and Development, and Transportation and Aerospace. As a veteran of GE Research and United Technologies, currently employed by General Dynamics, and founder and CTO of Oxford Analytics LLC, coupled with academic appointments at University of Maine and University of Southern Maine, Dr. Rall is uniquely positioned to observe the emerging needs for workforce development in the artificial intelligence and autonomous systems space. His personal research interests broadly include theoretical and computational electromagnetics, Bayesian inference, and its application to AI algorithm formulation, and the derivation of knowledge extraction from multi-domain sensor fusion. Dr. Rall, a Nova Scotian by heritage, received his PhD from University of Manitoba and his master's and bachelor's degree in electrical engineering from Technical University of Nova Scotia, Halifax, Canada. So please join me to welcome Walter to the podium.
Thank you very much, Ali. Good afternoon, ladies and gentlemen. Many thanks to the University of Maine AI Initiative and to my colleague, Dr. Ali Abidi, for inviting me to participate in the event today. My name, as Dr. Ali indicated, is Walter Roll, and I am chair of the IEEE Maine section, and I have a couple of jobs that keep me occupied through the day. My comments this afternoon are principally directed to those individuals who may be mid-career, looking to pivot their interests into a new area, or who may be looking for new opportunities because of the current global pandemic. However, my comments may provide useful insights to individuals at any career stage, from early experience workforce entry to those who wish to stay involved past conventional retirement norm. The objective of my talk today is to provide some practical, concrete guidance and advice and suggestions on where readily available resources may be found to at least develop an initial capability in the artificial intelligence, machine learning, autonomous system space. But before I get into those details, principally, as Dr. Ali had indicated, one of the sponsors of this event is the Institute for Electrical and Electronic Engineers. And I've thought for those on the call who are not IEEE members, they may be interested in a little background on the Institute itself. For those who do not know, the IEEE has approximately 420,000 members in over 160 countries. The organization is organized both geographically and by technical society. There's 334 sections around the world, and the IEEE Maine section, of which I am chair, is one of those 334. Within those sections are over 2,000 technical chapters that unite local members with similar technical interests. We have a number of affinity groups, consultants networks, and young professionals, women in engineering. And in the technical perspective, the IEEE is organized into 39 societies with 7 technical councils. For those of us in electrical engineering, we know that the IEEE is a treasure trove of documentation, and most of that is contained in the IEEE Explore Digital Library. We have many active standards and more than 500 standards under development. For those who are using a wireless connection for your laptop to listen to this talk this afternoon, the wireless 802.11 protocol that your laptop is using to talk to your router is in fact an IEEE 802.11. So across the board, from power distribution to computer communications to biomedical devices, the IEEE is very active in standards development. The organization publishes more than 200 transactions, journals, and magazines every year. And the IEEE transactions are considered to be the premier venue for the publication of refereed electrical engineering content. We have many conferences, conference proceedings, etc. And just in summary, a treasure trove of opportunity to learn and to explore and to research. So getting to the topic of my talk today, workforce development in the artificial intelligence and autonomous system space from an enterprise perspective, I like to think that there are 2 paths emerging in the area of AI careers. The first path involves the applications development, and the second path is more fundamental research and development. So as my 2 previous colleagues have indicated, there are a number of application domains: biomedical engineering, natural language processing, playing games such as AlphaGo. And the development of all of those applications are principally using well-defined tools or emerging well-defined tools that even those with a very introductory knowledge of the topic have somewhat ready access to. And I will get to that in a moment. However, on the other side, in the areas of research and development, the top picture here on the right is the hardware complement required for a self-driving vehicle that was implemented last year at MIT. And you can see for this self-driving or a semi-autonomous level 4 autonomous vehicle, you require a full trunkload of equipment to to actually affect those functions. So in the area of hardware development, NVIDIA, for example, had developed the graphical processing unit, the GPU, and have tailored that towards machine learning applications. Google has developed the TPU, or the TensorFlow processing unit, that has been developed more for the more efficient application of such activities. Dr. Vivian Z at MIT is conducting a number of research areas around the efficient development of new hardware architectures for artificial intelligence and machine learning. So there's many opportunities to pursue in that space. The little picture here on the bottom right actually speaks to some of the current challenges, for example, in machine learning directed towards computer vision and self-driving vehicles. The left column shown here shows a bus, a cheetah, and a pyramid of some sort. And when these photos are actually observed in the clear or without any distortion, they can be correctly identified fairly easily by a machine learning algorithm. However, if you introduce a little distortion into those photographs, as shown in the middle column here, in each of those situations, the bus is classified by the known machine learning algorithm as an ostrich. Similarly, for the cheetah, is classified as an ostrich, and even this pyramid is classified as an ostrich. Some recent research has indicated that machine learning algorithms directed towards this space can be somewhat brittle. My previous colleagues had talked a little bit about the bias that can be introduced in the data labeling exercise around these training approaches. So there is still plenty of research to be performed in the further development of machine learning, for example, and computer vision for self-driving vehicles. So my previous two colleagues talked about AI education at the university level. And I would like to give a slightly different perspective on what many will see as a new education model emerging. And that new education model was actually, I think, among others, established by Dr. Sebastian Thrun, and there's a photo of him from Wikipedia. Dr. Thrun was doing a lot of work in the self-driving space at Carnegie Mellon University with a small research group. He then transferred to Stanford University, where he continued to work in that area. And he became very frustrated at the inability of students to either get to Stanford or for a number of reasons, or seeming to not have interest in that area. Dr. Thrun took some may consider somewhat bold move in moving his entire curriculum online to teach the autonomous vehicle, self-driving vehicle, machine learning technology base, engineering base, to anybody essentially who wanted to study it. His concept was that there are brilliant people all over the world who would be very interested in developing this technology, and he wanted to provide the tools to them to do that. Hence the establishment of what is now referred to as Udacity. And if anybody now Googles, to use that verb that some people might find offensive at times, but it's just part of speech. If you Google Udacity, you'll see that they have many nano degree programs available for a number of topics. Now, to give you an idea of what's involved in the Udacity self-driving vehicle nano degree program, I've listed those on the left hand of this side. There's some very interesting education around advanced lane finding using computer vision techniques. Deep learning experts from NVIDIA give some terrific instruction around deep learning, with some practical examples around traffic sign classifiers and behavioral cloning. Extended Kalman filters and Bayesian inference particle filters are used for sensor fusion. There are localization modules to actually evaluate or kidnap vehicle. planning functions, and with an application of highway driving, and then finally a system integration module that helps the individual to actually program a self-driving vehicle. Now, Udacity is only one example of this space. Even before Udacity was launched, Andrew Ng at Stanford University through Coursera had a full series on machine learning. And that was actually fantastic because within that program, he set up Octave/MATLAB exercises where you could actually develop your own code and submit it to the server at Stanford, and it would grade your assignment for you and come back. And all of that Coursera course was actually free of charge. More recently, you might have heard that Google is providing the Google Certificate Program, where you do not have to actually engage in a 4-year university program to get a computer science degree and then go work with Google. You can get IT certifications through Google, and from a mid-career position, pivot and go directly into another area. And finally, the IEEE has their e-learning library series available, where you can pick a particular topic or put together a series of topics and discuss that. And I would even say within our own IEEE main section, over the last actually from September to December, I have organized a 4-part series entitled Deep Conversations About Deep Learning, where we address some of the more technical aspects around the mathematics behind artificial intelligence, technologies and challenges around self-driving vehicles, physics-based models, and AI for all of us, with some of our local resources in this area. So based on this idea that there, at least for the application space, there are opportunities to self-educate to some degree and at least become familiar with the technology. My next slide actually speaks to some of the resources available. I entitled this slide Application Education Resources Everywhere. Some pricey, some expensive, and some are absolutely free. So certainly the Udacity programs, I think they may be $200, and I'm not even sure, but they're not that expensive. There are many resources available through the IEEE Explore website. Amazon Web Services actually has one version of their compute platform where you can get 1 year free of charge. The American Physical Society has some free online resources. The Code platform is a free online code development base. The Society for Industrial and Applied Mathematics has opportunities. Of course, Coursera has a full catalog of courses, many of which are free of charge and have exercises associated. The MIT MIT OpenCourseWare is phenomenal. They have 2 programs I would highly recommend, Introduction to DeepLearning.edu and SelfDrivingCars.edu. With the Introduction to DeepLearning.edu program, they actually have a series of lectures, a series of guest lectures, and associated with each lecture is a lab assignment, and the lab assignment actually allows you to develop your own code in TensorFlow and exercise that on Google Colab. So even if you have some extra thing you want to try out, you can actually edit your TensorFlow code in Google Colab and run it. Of course, additional resources at Khan Academy. And if you want a MATLAB type environment, certainly you can use the GNU Octave resource, and that is, in fact, what Andrew Ng used for his machine learning course through Stanford and Coursera. So on the application side, there are plenty of resources for people at all career levels to at least get their feet wet, develop some interest, and then to pursue additional deeper understanding if they find that their vocation actually requires. However, in doing work in the research and development space, there are research and development education resources available, but it requires a little deeper understanding of what's going on to actually do, in my opinion, useful work in that space. And to illustrate that point, I present 3 examples on this slide. So on the top left here, my pointer showing For those that know about such things, this is a graphic depiction of a convolutional neural network, which is used principally for computer vision and for self-driving vehicles, for object detection and traffic sign classifiers, etc. And very briefly, I'll just describe how this works for those that don't know about such things. So a camera or a LiDAR will actually capture a two-dimensional frame of data which represents the image. That frame is actually scanned. A filter of sorts, so we call it a filter, is actually moved over a few pixels at a time, and it jumps along back and forth and back and forth. And the greatest value, or the maximum value of the pixels in that n by m space are actually compressed into what they call the pooling or max pooling chain. That max pool then is moved into a conventional neural network. The output of the conventional neural network will actually perform the classification of the image. The difficulty behind getting into some of the nuts and bolts and limitation of that architecture, I illustrate in the next equation. So what this depiction is trying to execute is actually this equation. And for the electrical engineers in the audience, you know, this is the standard equation for a convolution. Function f of t convolved with g of t is actually this infinite integral with the time-shifted version or an inverse version of the two functions. Undergraduate electrical engineering students will understand that you can actually do this graphically. And even when you do it graphically, you get a better understanding of the actual function and what resolution is required to get a valid output. But getting from the top one to the second one or to the equation requires a more than a simple understanding of TensorFlow. The second example that I will show is, so on the right-hand side of this graph, you'll see I have the cover of this book, The Nature of Statistical Learning Theory. This is a very famous gentleman by the name of Vladimir M. Vapnik. Dr. Vapnik is co-founder or co-inventor of a technique referred to as the support vector machine, which is a well-known approach in machine learning. The equation for the support vector machine is I give down here. Again, there's some advanced mathematical notation that you will need more than a basic understanding of TensorFlow or computer programming to recognize. And in fact, this is a Gaussian kernel that you'll see here. So getting to the roots of that will require some grounding in probability theory. And finally, if you're interested in Bayesian inference networks, you have to know what the Bayes equation is. And this is actually the Bayes equation here. So for research and development educational activities, we really need to go a little deeper, and it is certainly possible to do. But my takeaway is that a strong foundation is absolutely critical. And my other colleagues refer to this as well. A strong foundation, calculus, differential equations, linear algebra, numerical methods, probability statistics is really needed before you get into some of the finer points of research and development around artificial intelligence, machine learning, autonomous systems. Now, for the autodidactically inclined people in the audience, you certainly can purchase some textbooks and study much of this material yourself. There are other online resources. There are YouTube videos all over the place around some of these techniques. In fact, quite often I look for used copies of some of these textbooks, so I'm not spending vast sums of money on new textbooks, but I find that even the used copies are certainly serviceable and are excellent additions to my library. Fundamentals of calculus, fundamentals. In fact, the fundamentals of probability that I just saw the other day, you can get a copy of that, I think, for $10 a pop. An introduction to functional analysis as well, not particularly expensive. So I'm hoping that my comments today have actually given some practical advice on where those who are interested in pivoting into this space may find the resources to get them started. And if there's anything that I can do to provide some additional feedback or some assistance, I would be glad to do so. Many thanks to Dr. Abidi and the University of Maine and IEEE USA for inviting me to participate in this event. I hope that all of you are safe and healthy and that your families are safe and healthy. My contact information is in the lower left corner of the slide. And with that, I'm happy to take any questions. Ali, back to you.
Thank you very much, Dr. Rao, for the great presentation. I see some of the questions for our previous speaker has been already answered, but let me ask one question from Dr. Rao in the interest of time that we have. So one question is that from Alan, any thought on putting together a series of courses for existing workforce to learn or relearn math from middle school through college so they can work in AI and contribute to the AI projects?
So very briefly, because I see we don't have much time, the short answer is yes. Here, at least in the state of Maine, there's a STEM initiative with the Maine State Chamber of Commerce, and we're working on putting an adult sort of STEM education plan together.
That's very good. Actually, that kind of answers the second question as well. There is another question from Gabriella. Gabriella, thanks for joining us from Honduras. So the question is that, is there any initiative from IEEE in Maine to work with other sections related to the topic?
And in fact, yes, I understand, actually, Dr. Abidi advised me at our section meeting on Monday that IEEE Region 1 has launched the IEEE Region 1 Academy. So the slide decks that I had prepared for our Deep Conversations on Deep Learning series, I will move to the Region 1 Academy, and I will be available to represent those as the opportunities arise.
Thank you very much again. So that's all the time we have for today. Again, I would like to thank all the speakers for presenting excellent presentation for us, all the attendees from all over the world for joining us, and also our sponsors, IEEE Maine Communication and Computer Society Joint Chapter, IEEE Maine Section, IEEE Region 1, as well as IEEE USA. So stay safe, and hopefully we'll see you in our next AI webinar on December 3rd. You can look at the slides and the video recording on the AI website, which is ai.umaine.edu, which was also posted in the chat. And again, feel free to reach out to us. My email is abedi, A-B-E-D-I, @IEEE.org. And I will be happy to route your question to any speakers that you wanted. So thanks very much again, everyone, and have a great day.